All right, here we go. Video for today. We have an explore question to start. All right, it says much media attention has been focused on mammography of detecting breast cancer. Okay, the following table shows 10,000 women in their 40s, number of women with positive or negative mammograms, and the number who were diagnosed with cancer versus those who were not diagnosed for 10 years. Okay, so we have a series of questions to answer. All right, number one. Thank you. There it is. Shalom. Thank you. Number one, first question, it says, what percentage of the 10,000 women had a positive mammogram? Okay, so look here. Total with a positive mammogram was 6432. So I do 6432, and I divide that by 10,000. I apologize with the handwriting. I'm doing my best here. 6432 divided by 10,000. All right, I got 0.6432, which is about 64%. Okay, try the next one. What percent of the 10,000 women had a cancer diagnosis? All right. What percent of women of the 10,000 had a cancer diagnosis, no matter if their mammogram was positive or negative? So I'm going to look over here. Of our 10,000 women here, 378 had a cancer diagnosis. So it's 378 now divided by 10,000. Okay, 378 divided by 10, 1, 2, 3. Boom. 0.0378, which is about, we'll call it 4%. I'm going to round up to the nearest percent on all these. What percent of the women who had a positive, who had cancer, had a positive mammogram? So our first thing that we need to look at here is the number of women who had cancer. All right, so that immediately means I'm looking up here. All right, well, what percent of them had a positive mammogram? 302 of the women that had cancer. So the total women that actually diagnosed with the cancer within 10 years were 378. So really, it's the 10,000 does not come into play here. It's just 302 divided by 378, because all I'm concerned about now is the number of women that actually had or that were diagnosed with cancer. And that was about, I would say it was I got 0.7989, which is about 80%. So of the women that were actually diagnosed with the cancer within that 10 years, 80% of them had a positive mammogram. Okay. What percentage of women who had a positive mammogram had cancer? Okay. So now we're looking at just the positive mammogram here. Okay. What percentage of this total? So our total now, all of our positive mammograms were 6432. What percentage of those women were diagnosed with cancer? Only 302 of them. So again, that's 302 divided by the total number of women that tested positive, and they had a positive mammogram. So 302 divided by 6432 is 0.04695. So I'm going to say about 5%. Again, I should have said this at the beginning. How do I go from a decimal to a percentage? I just multiply by 100, or you can also move your decimal point over twice. Okay. Explain why the answers are not the same. What do these percents actually say? So I kind of talked through that. I want you to answer this question yourself. Okay. Why are these answers of 3 and 4 different? All right. I want you to try to answer that yourself. Okay, and I'm going to move on to the next one, and then we can talk about our answers to that question later on. All right. Again, I kind of explained that as we went along. Remember what we're looking at here in this question, we're only looking at the women that had cancer. Here we're comparing both with cancer and without. All right, so what's today about? Today's about probability. So in this section, we focus on what percent of the time an event happens and interpreting those percents as probabilities. You should focus on the following questions. So here are our questions for today. Do you remember how to find a percent? That's number one. We did that in the Explore. Why is relative frequency also considered a probability? And how is experimental probability different than theoretical? Okay. The percents you calculate in the Explore are considered relative frequencies because they tell us what percent of something that happened. Relative frequency is the number of times an event occurs. So relative frequency is the ratio formed when the frequency is divided by the total number. So if 15 women in a group of 75 are diagnosed with cancer, then the relative frequency of getting cancer in that group would be 15 over 75, which was 20%. Again, it says frequency can represent as a fraction, decimal, or percent. Okay. So each year, a general social survey asks respondents if they are working full-time, working part-time, or going to school, keeping house, and so on. In 1972, 1615 people responded. 750 of them were working full-time, and 121 of them were part-time. Okay. In 2014, 2538 responded. 1230 were working full-time, and 273 were part-time. Find the relative frequency of full-time workers and the relative frequency of part-time workers for each year, and how do they compare? All right, so our first one, we're in 1972. And now I want to find the relative frequency of the number of people working full-time. All right, well, there were 1615 people that responded, so that's my total. And for full-time, 750 for full-time. Okay, so I'm going to write full-time right there for FT. All right, 750 divided by 1615 gives me 0.464, which is about 46%. If I do part-time now, part-time would be what? You find the part-time frequency. Pause the video. You find the part-time. Go for it. All right, so I got part-time to be 7%. Okay. For 1972. Now, obviously, you would think in your mind, I would think that these two should equal 100. But we have to remember that there was also the option of going to school, keeping house, and so on and so forth. So there's other options. It wasn't just full-time versus part-time. Okay, so there's other options out there. So if I want to think about 2014, I want you to find the percentages of, the relative frequency of people working full-time in 2014 and the people working part-time in 2014. Go ahead and pause the video and do that, and I'll show my answers in a minute. All right, so I got 48% for full-time, okay? I did 1230 divided by 2538. No, 11%, about 11%, it was like 0.1075. So 273 divided by 2538 for that one. Okay, how do they compare? Well, if you look at the full-time workers, that increased, and the number of part-time and the part-time percentage increased as well. There was a greater increase in part-time workers versus than the full-time workers. Okay, so that's something like a comparison that you could do in your head. All right, or that's kind of like an answer I'm looking for. Let's do another one. A national survey asked how many people were living in a respondent's household. The following table shows the results. Find the relative frequency of households with 8 or more and interpret it. This is where the data was from. So we'll talk this out together. So I want to think about this household size, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? And these are the number of people that responded for having that number in their house. Now it says, find the relative frequency of households with more than 8 and interpret it. Well, that means that I care about all of these numbers here. And we're going to assume they want 8 included in there, so 8 or more. So realistically, I care about these numbers. Now, I also want to consider the total, because in order to find my relative frequency, I need to find the total. Okay? Well, I know that the number here, this is 6 people. All right, that's 6 of the respondents. Okay? The total is going to be the sum of all of this. It's going to be all of these numbers here added together. All right? So I'm going to add that up. I'm going to pause the video just for the sake of time, and I'm going to add those up. You do the same. Hopefully we get the same thing. All right. All right, so I got 25. Whoops. I got 2538. Hopefully you got that same answer there, 2538. Okay, and then I want to find that percentage times 100. So the percentage is about, it's 0.24%. So less than 1% of this data set, okay, of this national survey, of this data set, of the people that responded, all right, less than 1% of those people had more than 8 people in their house. Now that may not be realistic, okay. Obviously, it's a small sample size if only 2,500 some responded. Okay, experimental probability is what we're going to talk about next. It's kind of similar to relative frequency. Tells the likelihood or chance, or probability tells the likelihood or chance of something happening. Relative frequencies that tell us what percent of the time something did happen can also be considered experimental probabilities. These percents can be used to say what percent of the data we expect something to happen in the future based on actual data. All right, so this is an example of that. Okay, about a presidential survey, 40% of Americans approve of the job the president is doing. In other words, 40 out of 100, or 4 out of 10, or 2 out of every 5 Americans approve the job the president is doing. You can interpret this as experimental probability and say that if you randomly pick an American, you would expect to get someone who favors the president about 40% of the time. No, this is an older book, okay, so that may or may not be true. Who knows? All right, so what I want you to do, okay, it says recently a poll was conducted to try and understand consumer coffee habits. Complete the table and do the problems that follow it. So you need to copy this table down, and I want you to complete this, okay? Think about, here's the age range for 18 to 44, all right? Here's the number of people that drink at least a cup per day. Not sure what this is, that's on you to fill out, but here's the total. Okay, so I'm going to help you with this first one. Well, if the total is 744, and I know that 357 drink at least 1 cup a day, I would do 744 minus 357 to figure out that 387 people do not drink at least 1 cup per day. Okay, you obviously know how to find totals. Do that. So fill this table out, and then you're going to check your work in a minute. All right, here are my numbers there for you. Okay, so check your work, make sure our numbers match. All right, yeah. So it says find the experimental probability that someone in each age group drinks at least 1 coffee per day, and which one has the highest probability. You don't have to copy this down. I'm just going to use it to organize my work. So find the experimental probability that someone in each age group drinks at least 1 cup of coffee per day. All right. Sorry. All right. So what I want to do is go age group by age group here. So I'm going to do 357. Sorry about my handwriting. Divided by the total for that actual age group. So 744. And get my experimental probability, and so on and so forth. The next one is 342 divided by 519. And the last one I got 196 divided by 266. All right, go ahead and find out what those probabilities are, then come back and check your work. All right, here are my percentages. That's about 48. It was like 47 and some change, and that's about 66. and about 74. So the highest probability of someone having a cup per day is a 65 plus. Okay. I'm gonna, you would have yours filled out. I'm gonna bring my. All right. Find the experimental probability that someone over 65 does not drink. Does not drink at least 1 cup of coffee per day. That someone over 65 doesn't drink 1 cup of coffee per day. Go for it. And it also asks for the fastest way to do it. I would say just to do 70 divided by 266 is that's how I would do it. However, we found that 74% do drink a cup of coffee per day. So obviously the remaining 26% would be those that do not drink a cup of coffee per day. So if you already found the ones that do, the ones that don't would just be 100 minus the ones that do. All right, that would be the fastest way. Find the overall probability that someone 18 years or older drinks at least 1 cup of coffee per day. Well, 18 years or older is everyone here, 18 plus, okay? That includes every age group. So really, we're looking at our totals. So I'm looking at 913 here, divided by the total number of people that were surveyed, 1529. All right, so 913 divided by 1529, I got, it's, 0.597, which is about 60% of people over 18 drink coffee. I personally drink coffee. I drink about 2 to 3 cups a day, depending on the day. I go in waves. We have one more slide. I'm not going to do it. This video was long enough, I think. All right. This is just an application or another application that we could talk about. All right. Oh, Buckus, my phone's blowing up right now. So we'll call it a day on that. All right.